Welcome again. Today we will discuss ruthenium based reagents in organic synthesis. So, ruthenium is a fifth row element as you can see here, and it is in the same group with iron. And ruthenium chemistry is mainly the alkyl leading complexes which are used for metathesis catalyst. We will see. And also ruthenium has a property to take hydrogen. So, it can take hydrogen, and that is why it is useful for hydrogenation, oxidation reaction. So, we will see details. So, Grubbs catalyst has been very popular for metathesis catalyst, and there are several versions of this Grubbs catalyst. First one is first generation catalyst, which was first developed, then second generation catalyst, then Hoveda-Grubbs catalyst, third generation catalyst. In alkene metathesis, there are different versions are there: cross metathesis, ring closing metathesis, ring opening metathesis, polymerization ROMP, and acyclic diene metathesis, that is also polymerization ADMET. And as I told, hydrogenation also is possible with molecular hydrogen, enantioselective hydrogenation also possible, hydrogen transfer reactions both intra and intermolecularly, oxidation hydrogen transfer reactions also possible, and ruthenium oxide promoted oxidation, that is strong oxidizing agent, and isomerization also is possible, double bond isomerization we will see, and nucleophilic addition to carbon carbon and carbon hetero atom multiple bonds, that we will also see. So, first we will discuss Grubbs catalyst. Grubbs catalysts are a series of transition metal carbene complexes used as catalyst for olefin metathesis, and you know Grubbs got Nobel Prize for discovery of this catalyst. Grubbs catalysts are named after Robert H. Grubbs, the chemist who supervised their synthesis. Several generations of the catalysts have been developed. First generation catalyst we already told, second generation Hoveda-Grubbs catalyst, and third generation Grubbs catalyst. Grubbs catalysts tolerate many functional groups in the alkene substrates, are air tolerant, and are compatible with a wide range of solvents. So, that is why it is very useful. Both the first and second generation catalysts are commercially available along with many derivatives of the second generation catalyst. So, you can buy this catalyst. So, this is the first generation catalyst. The structure you can see, 2 chlorine is there, 2 PCOI3, and this is the benzylidene group is there. In the 1960, ruthenium trichloride was found to catalyze olefin metathesis. The first well defined ruthenium catalyst was reported in 1992. It was prepared from RuCl to PPH3 and diphenyl cyclopropene. So, this is the reaction, it was developed in 1992. First this catalyst was developed. So, you can see this is the starting material diphenyl cyclopropene, and this is the ruthenium Cl2 PPH3 and now this alkylidene bond was formed here. So, this is alkylidene bond, that is very important because this bond only reacts with the olefin, and in 53 degree centigrade 11 hours you get this catalyst. So, inspired by this study, then 1995 what is known as the first generation Grubbs catalyst. It is synthesized from RuCl to PPH3, phenyl diazomethane and tricyclohexane phosphine in a one pot synthesis. So, this is the synthesis RuCl to PPH3, then this phenyl diazomethane, then you get this one, this also is catalyst, but if you put now PCOI3 tricyclohexane phosphine, because those are more nucleophilic, so they can displace this PPH3 group and you get this. So, this is the first generation catalyst, Grubbs first generation. and this was reported in Angoo Chemie 1995. The second generation carbene, you can see the N-heterocyclic carbene is there, dihydroimidazole motif is present here, and this is the mesytyl group for the extra stabilization. In 1999, Grubbs reported the second generation catalyst based on a saturated N-heterocyclic carbene 1,3-bis 2,4,6 trimethyl dihydroimidazole. This is this motif, and this can be prepared from this first generation catalyst. If you put, because they are now more nucleophilic than PCOI3, so they can displaced one PCOI3 gets displaced, and then you get this second generation catalyst. In both the saturated and unsaturated cases, a phosphine ligand is replaced with an N-heterocyclic carbene, which is characteristic of all second generation type catalysts. Hoveda-Grubbs catalyst. In the Hoveda-Grubbs catalyst, the benzyl ligands have a chelating ortho-isopropoxy group attached to the benzene rings. The ortho-isopropoxy benzyl motif is sometimes referred to as Hoveda chelate. So, we will see the structure. So, this is the structure of Hoveda-Grubbs catalyst. And these are more expensive and slower to initiate than Grubbs catalyst from which they are derived, are popular because of their improved stability. So, they are more stable because here this isopropoxy additional binding with the benzylidene motif. So, that is why this is more stable. Hoveda-Grubbs catalysts are easily formed from the corresponding Grubbs catalyst by the addition of the chelating ligand and the use of a phosphine scavenger like copper chloride. This was published in JACS 2000. The second generation Hoveda-Grubbs catalyst can also be prepared from the first generation Hoveda-Grubbs catalyst by the addition of the NHC. So, from this first generation Hoveda-Grubbs catalyst, this is first generation Hoveda-Grubbs with phosphines are there. This is the PCOI3 is there. Now, you have to displace with this carbene, you can generate with potassium tertiary butoxide and this salt, and then in chloroform room temperature 2 hours you get this Hoveda-Grubbs catalyst. This was published in Tetraeden later. Third generation Grubbs catalyst is also there. The rate of the Grubbs catalyst can be altered by replacing the phosphine ligand with more labile pyridine ligands. So, here pyridine is present. By using 3-bromopyridine, the initiation rate is increased more than million-fold. The catalyst is traditionally isolated as a 2-pyridine complex. However, 1 pyridine is lost upon dissolving and reversibly inhibits the ruthenium center throughout any chemical reaction. So, this is the second generation catalyst, second generation Grubbs catalyst. And now, if you put the 3-bromopyridine X is equal to H or Br, then 2 pyridine motif attached, and this becomes, you can see, hexa coordinated. So, 1 pyridine can go out in the solution, and in the solution now it will become penta coordinated like usual, and this reversibly inhibits the ruthenium center throughout any chemical reaction. The principal application of the fast initiating catalyst is as initiators for ring opening metathesis polymerization. So, this is very useful for ROMP, ring opening metathesis polymerization, this third generation. Because of their usefulness in ROMP, these catalysts are sometimes referred to as the third generation Grubbs catalyst. This was published in Angoo Chemie 2002. Now, we will discuss different versions of alkene metathesis. So, olefin metathesis is an organic reaction that entails the redistribution of fragments of alkenes, olefins in the scission and regeneration of carbon-carbon double bond. So, carbon-carbon double bond are breaking and regenerated. Some important classes of olefin metathesis include cross metathesis, then ring closing metathesis, ring opening metathesis, polymerization and acyclic diene metathesis. Ruthenium complexes have been the most common catalyst used for the alkene metathesis. This is like cross metathesis. You can see one olefin is there, another olefin is there, then you put this Grab's catalyst. There are different generations are there, and now you get the cross product. So, one substance come from here, another comes here, and you get this cross product. So, these are the cross olefin or heterodimer. So, this is the overall metathesis reactions. If you have a diene like this is diene, then you can do the ring closing metathesis to get this one. This is cyclic olefin. So, a diene is converted to cyclic olefin by ring closing metathesis, and one molecule of ethylene is eliminated in this process, because this you can see 2 carbons are less here. Alternatively, if you put ring opening metathesis with ethylene, this cyclic olefin can be converted to this diene. So, this is called ring opening metathesis. On the other hand, if you do not put any diene, just with cyclic olefin, you put under this condition ring opening metathesis polymerization, you can get a polymer like this. And this diene also can be converted to polymer, that is called the acyclic diene metathesis polymerization. Here also ethylene minus NCH2 is eliminated in this process. And this is the cross metathesis that we have seen here, R1 substituted olefin, R2 substituted olefin, then cross metathesis you eliminate one molecule of ethylene and you get this heterodimer and this is homodimer. So, because this is from the same molecule reacting to give this one and this one reacting to give this one. Cross metathesis, we are interested in this heterodimer, because here you can get a olefin with both substituent R1 R2, and if you put this ruthenium alkylidene catalyst, then you can get this heterodimer, and these are the homodimer. So, the challenges are in the cross metathesis that must control homodimerization in order to obtain useful yields. So, if you want to get selectively the heterodimer, then this should be less. And EZ ratio are hard to predict and control, because here you can see a substituted olefin is generated. So, EZ stereochemistry should be an important. For tri-substituted olefin, ruthenium NHC catalyst has been mostly used. So, this is the second generation catalyst. If you have a tri-substituted here you can see here this is disubstituted olefin, and here also the tri-substituted olefin is generated. So, this is the tri-substitute forming, and in these cases it has been found that this second generation catalyst is very useful. Suppose if you react this one with 5 mole percent one, that is 5 mole percent second generation catalyst, you get 80% yield for this product. However, EZ ratio is 2.8:1. So, the selectivity is not very high, and this was published in Organic Letters. Also, with this ruthenium NHC catalyst, you can do cross metathesis of alpha beta unsaturated carbonyl substrates, like here this is alpha beta unsaturated A star, and with this here also a tri-substituted A star is forming, here disubstituted, here another substitution. So, total tri-substituted. So, this is tri-substituted, And here also this 5 mole percent catalyst, same catalyst is useful, and if you have a R1 is equal to hydrogen, then Ez is 4.5:1 with 91% yield. When R1 is methyl, then the yield gets reduced to 62%, but Ez ratio is higher than 20:1. So, this is very important that when you have a methyl substituent here, then the geometry is E. So, this is very important, and this was published in JACS 2000. Now, the mechanism we will discuss about cross metathesis. This was first proposed by Chauvin, who also shared the Nobel Prize with Graves in same year, and this mechanism was proposed in 1971. So, this is the catalyst and this is the first olefin. With this first olefin and you get with this catalyst, you get this metallocyclobutane. So, this is very important that metallocyclobutane is formed, because then only the redistribution will happen, and after that this bond will break and this will get a double bond. So, you get ethylene out, ethylene is eliminated and you get this one now with R dash. Now, a second olefin will come and second olefin will react with this alkylidene complex to generate another metallocyclobutane. So, two metallocyclobutanes are formed and through that only the redistribution happens and you get a heterodimer product. And now you get a heterodimer olefin product. Here the trans geometry has been shown and the catalyst is regenerated. So, catalyst is regenerated and you get a substituted olefin. Cross metathesis defined examples. Enine cross metathesis also is possible, like if you have this propargylic alcohol, chiral alcohol having 99% enantiomeric excess, and with this second generation catalyst, 5 mole percent of this catalyst in ethylene, 60 psi, dichloromethane room temperature, the enantiomer selectivity is retained 99% and you get 68% yield of this diene. So, this is conjugated diene is formed. We will see the mechanism later, but what I want to say now that these two carbon atoms this are here. So, this triple bond is becoming a single bond and these are coming from the ethylene. This was published in Organic Letters 2000. Ring closing metathesis, intramolecular metathesis of a diene to form a cyclic olefin. This is very important reaction. If you have a diene, then with a ring closing metathesis you can get this cyclic olefin. And RCM of small rings alcohols is also possible, allylic alcohols compatible with ruthenium catalyst. Suppose if you have this chiral alcohol with chiral center here and with 1 mole percent catalyst. So, this is first generation catalyst is enough for this reaction here, and 1 mole percent of this catalyst in dichloromethane 97% yield of this cyclopentene. So, cyclopentene is formed and these chiral centers are not disturbed in this process. So, this is very important and this was published in JOC 1996. Some more examples of ring closing metathesis, allyl ethers and acetals, both molybdenum and ruthenium catalyst tolerate these functionalities. Like here you can see this is acetal. So, this is acetal. So, you can see this acetal gives this cyclic acetal and cyclization happens with this catalyst. So, this is first generation variant and with this catalyst you can get this product in 87% yield. So, this is very useful reaction. This was published in JACS 1993. What is the mechanism of ring closing metathesis? So, if you have a diene like this, then this comes catalyst which already reacted. This catalyst comes and to get this metallocyclobutane, And after ethylene elimination, so here if you do this, then the ethylene get eliminated and you get this one. Now, this will react with this olefin, because this is accessible now to this olefin compared to other starting material, because intramolecular will be faster always, intramolecular faster than intermolecular. So, this will react with this olefin and you get this metallocyclobutane, and we generate this active catalyst. So, this is the active catalyst. To this active catalyst and you get your product. So, this is the product, cyclic olefin product is formed. So, overall and acyclic diene is converted to cyclic olefin by ring closing metathesis. Small rings also possible like amines. Here primary and secondary amines, they are incompatible with Grab's catalyst. So, primary secondary amines cannot be used. So, this is very important because they are basic, they might react with the catalyst, and tertiary amines typically tolerated by molybdenum and ruthenium catalyst, but they can be also problematic. Like here this tertiary amine, this is tertiary amine, this with catalyst 2, this is the first generation and this is 3 is second generation, and this is molybdenum catalyst 1. So, with catalyst 2 no reaction. Interestingly, if you destroy the nucleophilicity of this tertiary amine by this salt formation. So, if you make a salt now with 4% of catalyst 2, you can get this ring closing metathesis and you get this 5-member ring heterocycle in good yield. Also, you have to work up with sodium hydroxide. Also, for large ring formation, one molybdenum catalyst has been found to be useful. So, here tertiary amine, this is again tertiary amine and large ring formation, large ring. Here is 7-member ring is formed, 7-member heterocycle is formed with this molybdenum catalyst. When it is secondary amine salt, so now this is secondary amine salt, secondary amine salt and 5 mole percent 3 second generation catalyst in dichloromethane 40 degree centigrade 24 hours, you get only less conversion. So, tertiary amine salt is very good for the cyclization, but secondary amine salt is not good for the cyclization reaction. These are the papers JAX 1992, JAX 1993 and JOC 2000. RCM of small rings, carbonyl. So, carbonyl groups are also very useful functionality present in many natural products. So, if you get the carbonylated cycles, that could be useful. Like ketones, if you have, they are inert to ruthenium catalyst, typically tolerated by molybdenum catalyst, but olefination can occur. Carboxylic acid and aldehydes tolerated by Grab's catalyst, but not by Schrock catalyst. Esters, they are compatible with, so esters are very useful, they are compatible with both ruthenium and molybdenum catalyst. Synthesis of alpha beta unsaturated lactones from acrylate esters, ruthenium NHC catalyst. So, here you can see this alpha beta unsaturated ester when reacts with catalyst. So, this is also second generation catalyst. This is a double bond is there of course. So, second generation variant, and you get this 6-member lactone, 6-member lactone. So, cross metathesis happens. So, as I told, esters are very useful for this cross metathesis. Here also alpha beta unsaturated ester is present, and now these two carbon atoms will cycle. So, you get a 5-membered lactone here, this is 5-membered. Also, if you have a substitution in the double bond, that case also reaction works for 5-membered and you get good yield for this product. And if you have a substitution at both olefin, then also you get good yield of this product. This is also 5-membered lactone, 5 member lactone with double bond substitution. So, this was published in JOC 2000. Some more example RCM of small rings amides, like here this is alpha beta unsaturated amide, you can see here, and with second generation the similar catalyst that we have told earlier, second generation variant, you get 5 membered lactam, 5 membered lactam is formed in 82% yield. This was published in JOC 2000. Also phosphorus atom can be incorporated, new ruthenium NEC catalysts are compatible with phosphinic acids. So, this is the catalyst second generation variant, and this has been found to be useful for this cyclization reaction. This is the phosphinic acid, phosphinic acids, and these two double bonds can be cyclized to get a 5 membered ring, and this was published in Organic Letters 2000. Some more examples, and now we will discuss RCM of small rings, enine metathesis. Enine metathesis, alkylidine migration reacts from the alkene part to alkyne carbon. Like here, if you have a double bond, earlier it was both double bond, now if you have a triple bond, then the enine metathesis will happen, and here you can see that nothing is eliminated because R1, R2 are all staying in the product. So, product is of higher mass compared to cycle. Earlier only cycle was formed, here what happened, the exocyclic olefin. So, this is very important, exocyclic olefin is formed, and we will see the mechanism now. So, this reacts with the activated catalyst to generate this triple bond, reacts first to get this metallocyclobutene. Now, this will break like this and this will form. Now, this will react with this one, because as I told, the intramolecular will be faster to generate this metallocyclobutane. Cyclobutane will form with this double bond present, and now this will eliminate and give this product. So, this is the product, and this is also conjugated diene with the exocyclic double bond is present, and you get this is the catalyst back. This was published in Organic Letters 2000. RCM of small rings, enine metathesis. Enine metathesis examples, like here you can see there is a double bond is there, this is a substituted alkyne, and what will happen when it reacts with 1 mole % first generation catalyst, this is first generation catalyst, N can be 0, 1, 2, you get this product, cyclized product with this double bond here, and this is the conjugated diene, and this substance is present. So, nothing is lost here. This was published in Seedland 1994. Synthesis of epilacnine. So, this cross metathesis has been used in many natural product synthesis. One example is this epilacnine. This one is large ring, the product. And this is the starting material, you can see this is A star, also a NF group is there, and these terminal olefins are present with 5 more % PCOI3Cl2 Ru double bond CHPH, that is the first generation. So, first generation works for this enine metathesis, and this is the cross metathesis of course. So, you get this cyclization, and this is large ring, and the product is formed in 89% yield with 2:1 E to Z stereochemistry. Actually, whatever structure is shown, this is Z, but E is major. So, E is formed in 2:1 ratio. This was published in JACS 1999. Ring opening metathesis. Now, we will discuss ring opening metathesis. So far, we have discussed ring closing metathesis. Now, we will discuss ring opening metathesis. Ring opening of strained cyclic olefin. So, that should be strained to give open chain metal carbene provides driving force for ring opening metathesis. Selection of catalyst decided by functionality in the substrate. Use of terminal olefin results in exclusive formation of monosubstituted diene, however, EZ ratios are low. So, this is important that EZ ratios are low if you use of terminal olefin. So, here this cyclic olefin is reacted with the active catalyst, you get this. And now, if this cyclic olefin only reacts, then you get the ring opening metathesis polymerization, that is called polymer. Alternatively, if you put other acyclic olefin, then you can get ring opening metathesis. So, no polymerization happen, because here you are quenching with another olefin, then you get cross products. So, that both examples we will see. So, cross metathesis selectivity. So, this is the reaction is happening, this is the active catalyst which reacts with the cyclic olefin, this is strained, as you can see here, this is bicyclic compound, this is strained here, and now this will open, and this active catalyst, you can see one part is going to one carbon, another part, this double bond shear coming to the another part. And now, if you react with acyclic olefin, so this is the acyclic olefin, then you can get this cross product. So, this is the cross product. So, this is cross product, and this has used many applications. This was published in Tetrahedron 1997. Ring opening metathesis examples. So, this is the acyclic olefin here, acyclic olefin. This is allylic acetate, and this is the symmetrical diol. So, symmetric diol. One advantage is symmetric diol, that you do not get mixture. Here, that is why the substituents are different here, but you do not get mixture, because these two are same. And as you can see, as I told earlier, this olefin, one part will go to here, this CH2OH is missing, another part will come here. So, one part is going here, that CH2 part, and this part CH2OH is going here, and you get this product with Grubbs catalyst 58% yields. This was published in Angochem in 1997. Also, this one is not symmetric. So, this is not symmetric. And in this case, this is the acyclic olefin, 1 octene here, 10 mole % Grubbs catalyst, mostly the first generation. Because this is now not symmetric, so when there is a symmetric, then you get one product. If it is not symmetric, then you get mixture product. So, this product is forming 53% yield. One case the methoxy has this substituent, on the other hand methoxy has this substituent. So, 53% yield for this one might be for the steric region, and with this is forming, this one is forming in 13% yield. This was published in JACS 1995. Now, we will discuss ring opening metathesis polymerization. Certain metal carbene based metathesis catalysts can polymerize strained cyclic olefins. Their sensitivity to air and potting media severely limits their application as living ring opening metathesis polymerization ROMP catalyst. Like this, the cyclic olefin react to this active catalyst, and you get this polymer. RuCl3NH2O has proven to be effective ROMP catalyst in potting media such as water, and this is an example. Suppose this is the symmetrical olefin, and this one with ruthenium chloride water, you get this polymer. So, this is very important reaction, and it was published in Tetrahedron Letter 1986. Now, we will discuss acyclic diene metathesis polymerization, what is called ADMET, Acyclic diene metathesis or ADMET is a special type of olefin metathesis used to polymerize terminal dienes to polyene. So, if you see this is olefin, here one side is there, another side another olefin is there, and if you put ruthenium catalyst, this is Grab's second generation catalyst and this is Hoveda-Grab's catalyst. And if you put this diene with this ruthenium catalyst and after the elimination of ethylene you get this polymer which is called PPV. So, this is polypropylene vinylene and N-1 molecule of ethylene is eliminated. So, here N-1 is there. So, what could be the mechanism of this reaction? So, this catalyst after reaction with ethylene will generate this active catalyst and then this will react with this monomer and to generate the metallocyclobutane is formed and this metallocyclobutane after elimination of ethylene it will generate this active intermediate and this again will react with another molecule of monomer to generate another metallocyclobutane intermediate and this is highly trans and after that this again gets eliminated to generate this is the active catalyst and you get this trans olefin. So, this is dimer and now if you see this structure if this is X then this again reacts with X it will generate the trimer and trimer again will react with X then will generate tetramer. So, like this the polymerization will happen and N molecules of monomer after elimination of N-1 ethylene it will generate the polymer having N molecules of this monomer. So, R is equal to NC8H17 or 2-ethyl hexyl etc. Hydrogenation with molecular hydrogen, chemoselective hydrogenation, selective hydrogenation of cyclic trienes to the corresponding cyclic monoolefins have been studied using RuCl2CO PPH3 RuCl2 PPH3 and RuCOD COT catalysts. Like here there are 3 double bonds are present and with this catalyst with hydrogen 14 atmosphere pressure 158 degree centigrade benzene solvent you get this olefin. So, 2 double bond gets reduced. This was published in JOC 1973. Now, we will discuss hydrogenation with molecular hydrogen and chemoselective hydrogenations are possible. Due to the strong affinity of ruthenium toward heteroatom compounds, low valent ruthenium complexes act as efficient catalysts for reduction of a variety of carbonyl compounds. Aldehydes, ketones, carboxylic acid ester and carboxylic anhydrides can be converted into the corresponding alcohols with various ruthenium complexes under hydrogen pressure. So, as I have told that ruthenium can take up hydrogen and it can then the hydride can be transferred. Like here this is alpha beta unsaturated aldehyde. This when reacted with this RuCl3 P sulfonate ester is there, phosphorus has this sulfonate ester derivative with this is the catalyst and toluene buffer hydrogen. So, hydrogen will be taken up by ruthenium first and 35 degree centigrade you get this allylic alcohol. So, allylic alcohol is formed in 97% conversion with 99% selectivity. So, what could be the mechanism? As I told the ruthenium will take up the hydrogen. So, HRuCl is the active catalyst here and HRuCl will react with first the carbonyl, it will bind like this because this is also Lewis acid, ruthenium also Lewis acid. So, it will bind with carbonyl, and now the hydride will deliver to the carbonyl and it becomes alkoxy. So, this ruthenium oxygen bond will form now, and now hydrogen will come to make this hydride, because ruthenium always will take up hydrogen, and again another hydride will transfer to oxygen and this bond will break. So, you get HRUCl, HRUCl is here present and you get the allylic alcohol. So, this is the product. So, as you can see, HRUCl is the active catalyst which will bind to the carbonyl, then the transfer the hydrogen, and again hydrogen will come to make this dihydride ruthenium, then the hydride will transfer to the oxygen and the alcohol will form. This was published in Organometallics 1991. Enantioselective version also is possible. Suppose if you use chiral catalyst, then enantioselectivity can be obtained. Like this one, this is the alpha beta unsaturated carboxylic acid, and with ruthenium acetate, this is the chiral ligand, BiNAP chiral ligand. So, PPH2, this is chiral, this is the BiNAP, and with H2 135 atmosphere you get this product which is useful drug S-naproxen in 97% E. This was published in JOC 1987. Also this anhydride and this double bond is present. So, the double bond will be selectively reduced because you generate a chiral center with RuCO2 R BiNAP catalyst and hydrogen 20 atmosphere, you get 95% yield. This was published in JOC. Also this one, there is a stereogenic center will form here after the reduction. This is the beta keto ester, and with RuBr2 R BiNAP catalyst H2 100 atmosphere, you get this product. So, 2 chiral center, because after reduction this center is stable with 98% E. Also this cyclic beta keto ester with RuCl C6H6 R BiNAP chloride catalyst H2 100 atmosphere 50 degree centigrade, you get this beta hydroxy ester in 93% yield. This was published in JACS 1989. Hydrogen transfer reactions also is possible. Alternative method for hydrogenation of organic substrates is hydrogen transfer reactions from an organic hydrogen source, where the hydrogen is supplied by a donor molecule DH2, which itself undergoes dehydrogenation during the course of the reaction. So, in this case hydrogen transfer reaction, the external hydrogen is not required. Oxidative addition of alcohols to low valent metal complexes and the subsequent alpha hydrogen elimination gives carbonyl compounds and metal dihydrates. The metal dihydrates react with a hydrogen acceptor to afford hydrogenation product AH2 and metal complexes to complete the catalytic cycle. So, here what will happen, the DH2 which wants to give hydrogen to the acceptor will take the hydrogen AH2 and D will form. So, what will happen, D will be oxidized. So, in this process D is getting oxidized and A is getting reduced. And this is the cycle. So, suppose here in this case this alcohol is actually DH2. So, this is the alcohol which is DH2 and AH2, A you have to use, that we will see, sometimes enone is present. And what will happen, this metal takes up the hydrogen from the alcohol to convert the alcohol to aldehyde and it will become MH2. MH2 will transfer hydrogen to acceptor, because MH2 has to be converted to again M, so that it can take up the hydride again. So, MH2 has to be free, and that process is only possible if you put another acceptor who will take up the hydrogen, so that MH2 will convert to M again. And the example is this. Here interestingly this alcohol will be oxidized. So, this is like a redox reaction, because internal redox reaction, because here this alcohol is getting oxidized and this double bond is reduced. So, both acceptor and donor are in the same molecule, and with RuCl CP PPH3 whole 2 catalyst, this is the additive triethylamine H PF6 and dioxane 100 degree centigrade, you get 93% yield of this product. So, double bond get reduced and alcohol get oxidized, and this part is not affected. This was published in JACS 1993. Now, we will see this kind of transfer hydrogenation application of alcohol to ester. So, alcohol can be converted to ester also. The principle of the hydrogen transfer reaction has been applied to a variety of oxidative transformation of alcohols with low valent ruthenium complex catalyst. One of the typical reaction is the transformation of primary alcohol to the corresponding esters. When primary alcohols are allowed to react with low valent ruthenium catalyst, a similar dehydrogenation reaction occurs to give aldehyde and ruthenium dihydride. The aldehyde intermediate is trapped with the second molecule of primary alcohol to give hemiacetal. Further dehydrogenation of hemiacetal with ruthenium catalyst give the corresponding ester. So, as you know, the alcohol, suppose this is the alcohol, this will convert to aldehyde, and now this aldehyde will react with the alcohol to generate this hemiacetal. And now this hemiacetal will be oxidation, will give this ester. The low valent ruthenium complex is regenerated by the hydrogen transfer reaction of ruthenium dihydride to hydrogen acceptor to complete the catalytic cycle. Without hydrogen acceptor, generation of molecular hydrogen occurs via reductive elimination from ruthenium dihydride. So, this is also possible. If you do not put the hydrogen acceptor, then the hydrogen gas will eliminate, that is also possible if you have the system where the hydrogen can be eliminated. So, this is the catalyst, and now the alcohol will react, and this alcohol hydrogen will go to the ruthenium. So, RCHO will form. So, 2 hydrogen goes to the ruthenium. Now, if you put the acceptor, so without acceptor hydrogen will be eliminated. Now, if you put the acceptor, then the acceptor will take up the hydrogen, it go to AH2, and you have this complex. Now, again this RCH2 will react to generate the hemiacetal. So, this is hemiacetal, as we have shown here, hemiacetal will form, and this hemiacetal again will get oxidation. So, here the hemiacetal is getting oxidized, RCHO, OCH2R, and you get this ester and you get this ruthenium hydride. And again this acceptor will come. So, acceptor will take up the hydrogen. Whenever ruthenium has excess hydrogen, the acceptor will take up the hydrogen, so that the metal can again take up the hydrogen from the substrate, and in this process you can get the ester. Now, we will see some examples of this kind of reactions, like here 2 alcohol is there. So, this is a diol with RuH2 PPH3 whole 4. So, this is already hydride catalyst, because hydride is present here already, hydride catalyst, and acetone. So, this is the A. So, this will take the hydrogen. So, acceptor is here acetone, because acetone can be reduced to alcohol, and 180 degree centigrade toluene you get this lactone in 95% yield. This was published in Tetrahedron letter. Also, if you have this benzylic alcohol 2 equivalent with this ruthenium carbonyl cyclopentadiene carbonyl complex, catalytic amount 145 degree centigrade, you can get this ester, and hydrogen gas is eliminated. So, here no acceptor is, but hydrogen has to eliminate, and turnover number is 450. It was published in Journal of Organometallic Chemistry 1985. If you have a diol like this, one primary secondary, then the primary alcohol will be oxidized to the aldehyde first, and then this will react. So, lactol will form. So, this is going via this is the lactol. So, lactol is forming, and this lactol is converted to lactone, and here the acceptor is acetone. With this ruthenium hydride catalyst toluene 180 degree centigrade, you get this product 98% yield. This was published in JOC 1987. Some more example of oxidation, hydrogen transfer reaction. The hydrogen transfer reaction can also be applied to oxidation of alcohols to aldehydes and ketones. Various aliphatic and acyclic secondary alcohols are converted into the corresponding ketones upon heating with low valent ruthenium catalyst and hydrogen acceptors such as benzylidene acetone and acetone. Like here, the diol is converted to diketone with this catalyst, same catalyst, and this is the acceptor. It is the acceptor of hydrogen, and 135 degree centigrade you get 100% yield, almost quantitative yield, and this was published in JOC 1972. This is the indole derivative, and here with this catalyst, this is the acceptor. Potassium carbonate is base, 56 degree centigrade you get this compound in 91% yield, the alcohol oxidation. This was published in Chemcom 1992. Now, we will discuss ruthenium oxide promoted oxidation. Earlier we have seen that TPAP reagent where ruthenium 7, that time we told that TPAP is a mild reagent. On the other hand, ruthenium oxide, ruthenium is in 8 oxidation state. So, it is quite strong. Ruthenium oxide shows specific power of oxygenation and hydrogenation abstraction toward a variety of organic compounds. Hydroxy compounds undergo abstraction of activated R hydrogen atom followed by electron transfer to afford the corresponding carbonyl compounds and RuO2. So, it is converted after oxidation to RuO2. This is 4 oxidation state and this is 8. Here this alcohol is converting to ketone, secondary alcohol converting to ketone, and 2 molecule of water is eliminated. The reaction with olefins gives cyclic ruthenium 6 diester, which are converted into carbonyl compounds via oxidative cleavage of the carbon-carbon double bonds. So, this is very interesting. Ruthenium tetroxide with reaction with olefin to generate this ruthenium diester. So, this is diester, and this diester then cleaves like osmate ester to generate the ruthenium dioxide, and 2 molecules of ketone is formed. So, this is a very important reaction. Also, substrates bearing unactivated CH bonds such as alkanes and amides undergo hydrogen abstraction and the subsequent oxygen rebound to afford the corresponding hydroxy compounds, which are normally converted into the carbonyl compounds by second oxidation. So, ruthenium tetroxide reacts also with alkane to generate this ruthenium hydroxide compound, and you generate the alcohol. The alcohol is converted to the carbonyl compound again by oxidation, and this work was published in JOC 1996. Some more example of ruthenium oxide promoted oxidation. A stoichiometric amount of ruthenium oxide prepared readily by the reaction of RuCl3 or RuO2 with sodium periodate has been used for the oxidations. The reactions can be performed conveniently in a biphasic system. Like here in the aqueous phase, the RuO2 is getting oxidized to RuO4, the aqueous phase. Now, it is going to organic phase. RuO4 is going to organic phase after oxidation from RuO2, and now in the organic phase it is oxidizing substrate to SO, substrate oxide. Examples: very slow and incomplete reaction have often been encountered in the oxidation of RuO4. These sluggish reactions are due to inactivation of ruthenium catalyst with carboxylic acid by forming a low valent ruthenium carboxylate complex. The inactivation can be prevented by the addition of acetonitrile, and thus these solvents are used. We will see some examples. Acetonitrile, suppose this olefin, if you put with ruthenium chloride catalyst, sodium periodate, CCl4H2O, you get A, that is the starting material remain, and you get the aldehyde 17% yield. On the other hand, if you use CCl4H2 acetonitrile solvent 2:3:2, then you get this acid in 88% yield. So, that tells that acetonitrile is very important for converting olefin to carboxylic acid. This was published in JOC 1981. Some more examples, like here the secondary alcohol getting oxidized to the carbonyl here. So, ruthenium oxide and NaIO4 which in situ from the this is the additive, you get the 97% yield for the product. This was published in JOC 1987. Here also an important reaction, that benzene getting oxidized, this is phenyl, and this phenyl group getting oxidized to the first carboxylic acid. So, one carbon only remains, and that can be converted to the ester with diazomethane. So, this is very strong oxidizing agent. RuCl3 NaIO4 carbon tetrachloride water acetonitrile solvent, you get 85% yield for this product. This was published in Synthesis 1983. And the olefin can be cleaved as we have seen earlier with this system NaOCl. Here dichloromethane water is enough to give this diacid in 86 to 95%. This was published in Chemcom 1970. And if you have a amido group and OH group, then this kind of reaction is happening. The cyclization happens first and then the bond isomerization, as you can see, bond breaking and making here. So, you get this imine, and after hydrolysis you get the amide. So, amide is formed, PFCONH2 is formed. This was published in JACS 1994. Now, isomerization also is an important reaction in organic chemistry, and ruthenium can take up the hydrogen and transfer. So, as we have seen, so this isomerization can be carried out by ruthenium complexes, and generally low valent ruthenium complexes act as efficient catalyst for isomerization of beta gamma unsaturated oxygen and nitrogen containing compound, since ruthenium hydride intermediates have a strong affinity to promote hydrometallation of olefins and beta elimination of ruthenium hydride. So, like this, the ruthenium hydride first will hydrogenate this one and add like this, and now this hydrogen will be take up. This hydrogen will be take up, so the double bond will form and ultimately minus RuH, you get the isomerized product. So, this is isomerized. Examples like here. So, this is alpha beta gamma. So, this is beta gamma unsaturated ether, and when you put this ruthenium catalyst, you get this alpha beta unsaturated ether. So, this you can see, this is a Claisen substrate, O allyl and O vinyl. This is O vinyl, this is O allyl. Now, the Claisen rearrangement will happen like this way, and you get this aldehyde 92% yield. This was published in JOC 1977. Some more examples. Suppose if you have a double bond here, then you can get the conjugated with the phenyl olefin is forming here with polystyrene, this catalyst mesitylene solvent 140 degree centigrade. This was published in JOC 1981. Also, this one will convert it to alpha beta unsaturated. So, what we have seen, the beta gamma, if it is there beta gamma, then it goes to alpha beta. That is the reaction is happening, because this is more stable product, and here cis product is forming with this catalyst already hydrogenated and benzene 80 degree centigrade, 92% yield of this product. Also, this is an homoallylic alcohol. So, homoallylic alcohol, and this homoallylic alcohol, when treated with this catalyst RuCl2 PPH3 whole 3 and H2O, this is very important, in water solvent 90 to 100 degree centigrade, then you get allylic alcohol. So, what could be the mechanism of this reaction? Now, hydrorutheniation and beta hydride elimination give the allyl alcohol hydrido complex. Pi-allyl ruthenium complex is formed through the carbon oxygen bond cleavage of the allyl alcohol. For the nucleophilic attack of water, so this is very important, nucleophilic attack of water as less hindered side of pi-allyl ruthenium complex affords the stable complex which gives the product and ruthenium hydride to complete the catalytic cycle. So, this is the mechanism, this is the homoallylic alcohol. Now, in the double bond, this ruthenium hydride will add. So, ruthenium hydride will generate and attack the double bond, and then you can see the migration of the double bond happens. So, double bond has become now internal, and it will be coordinated with ruthenium hydride, and after elimination of water, this pi allyl ruthenium will form. So, this pi allyl ruthenium intermediate is very important, and water then attacks, because this is an electrophilic species and water can attack and mostly attack this side to generate this allylic alcohol, and where the double bond is coordinated with ruthenium hydride, and after elimination of ruthenium hydride you get this allylic alcohol. So, this is an important reaction, and this was published in JACS 1995, page number in 12867. Lastly, we will discuss nucleophilic addition to carbon-carbon and carbon heteroatom multiple bonds. First, we will discuss nucleophilic addition to alkynes. Terminal alkynes undergo regioselective nucleophilic addition of carboxylic acid upon heating with various low valent ruthenium complexes catalysts such as RuCl3, RuCod, RuCl2 arene and Ru3CO12 to give the corresponding enols. So, like this you can see this is alkyne and this is carboxylic acid. So, this is the nucleophile, and with ruthenium catalyst in the triple bond you can add this. So, you get A star. So, A star is formed after addition of carboxylic acid, and the mechanism is that this is the catalyst, it is first reacting with the alkyne to generate this, and after the activation now the addition will take place. So, OCOR2. So, acid is OCOR2. So, this is acting, this minus, this is the nucleophile, this minus is adding here, and you get this vinyl A star, and after protonation you get this olefin, and of course, this will isomerize, this can isomerize to the ketone RCOCH3, R1COCH3 after hydrolysis. So, like this one you can see the hydroxy and the triple bond is present, and if you treat with acetic acid with this complex carbonyl PPH3 catalyst in toluene 90 degree centigrade. So, what happens here, the alcohol is converting to acetate, also this triple bond is converting to the ketone, and here what is happening, now here this is the intermediate of course OAC. So, this is converting to the first this OH is forming, this is going to OH, and this OH is going to carbonyl. The enol is converting to carbonyl, and you get this product in 94% yield. This was published in Chemcom 1994. Nucleophilic addition to carbon-carbon heteroatom. So, now we will discuss CN triple bonds of nitriles. Transformation of cyanofunctionality with nucleophiles have been useful synthetic methods for the preparation of a variety of carbonyl compounds. However, the method often encounters the limitation of acidic conditions that are required to activate rather unstable CN triple bonds. Low valent ruthenium, like earlier, low valent ruthenium complexes have proven to show remarkable Lewis acidity and high efficiency for the activation of CN triple bond to nitriles. So, here you can see the triple bond C, that is the nitrile. So, nitrile bond is getting activated by ruthenium, so that the nucleophilic addition will take place now at the carbon center. Examples like here CO2Me and cyano group is there with water, water is the nucleophile, and with this catalyst RuH2 PPH3 catalyst DME solvent 120 degree centigrade temperature, you get this amide in 93% yield. So, what happens, C triple bond N, it adds water. So, what happens, OH adds here and it becomes C double bond NHR, and this after tautomerization this becomes C double bond O NH2. So, So, this is the amide. Cyanide is getting converted to amide, and this was published in JOC 1992. So, today we have discussed ruthenium catalyst, and first we have discussed the Grubbs cross metathesis catalyst. So, Grubbs first generation we have discussed. First generation has the benzyl lead substituents and cyclohexyl phosphine. On the other hand, second generation has the more nucleophilic N heterocyclic carbene, and third generation has pyridine, and this third generation catalysts have been found to be useful for ring opening metathesis polymerization, and Hobe the Grubbs catalyst where also the isopropoxy group is present, which is binding to ruthenium and giving extra stability. And we have seen different kind of metathesis reaction, cross metathesis we have seen, then the ring closing metathesis, and in the ring closing metathesis we have seen that different substituents can be tolerated, like esters are very useful substrate, also carboxylic acid. So, esters can be converted to lactones, because after cyclization we call it lactone, and these processes are very efficient to generate cyclic compound. Also ring closing metathesis we have seen for the synthesis of larger rings. One challenge is the EZ stereochemistry. Then we have seen the ring opening metathesis polymerization. In the ring opening metathesis polymerization, we have seen that with symmetrical olefin, if you put an acyclic olefin, then you can get a single product. On the other hand, if it is not symmetrical, if the double bond turns cyclic, if it is not symmetric, then you get a mixture of products depending on the steric. And ruthenium can take up hydrogen, and this chemistry has been exploited in many reactions like oxidation reduction. We have seen the reduction of aldehyde functionality, like alpha beta unsaturated aldehyde can be converted to allylic alcohol. Also double bond can be reduced with ruthenium catalyst, and we have seen that with BiNAP ligand and with hydrogen as the reducing agent, you can generate chiral center of alpha beta unsaturated carboxylic acid. You can get very high enantiomer selectivity. And then we have seen that this system can be also useful for oxidation. In the oxidation case, we have seen that it can be used with an acceptor like acetone or parabenzoquinone, which take up the hydrogen liberated during the oxidation process. And in this way, we have seen the oxidation of alcohol to esters. And lastly, we have seen the isomerization. So, isomerization of beta gamma unsaturated alcohol or amines can be converted to alpha beta unsaturated efficiently via this isomerization process. Thank you.